Okay, now I'm going to discuss you with about a problem, an example. We'll look at how can we solve this example. So here we have a beam. Determine the member end moments and reactions for the continuous beam shown in figure below by slope deflection method. As you can see that here you have a fixed support at A and a roller at B and a roller at C. So total unknowns are, like, if you consider the number of unknowns reactions, here you have 3 reactions at a fixed support, here 4, 5. So R is greater than 3, which means you cannot statically determine the external reactions. So external reactions cannot be solved using equilibrium equation. So that's what we define as they are statically indeterminate. So now we are going to look at how can we solve this problem using slope deflection method. So in slope deflection method, as we have discussed yesterday, this is the equation. This is the generic equation, and you derive a set of equations for each segment. So before we do that, what I want to do now, I would like to draw the free body diagram. So, and I would like to do a little. So this is my free body diagram. Here I have RA, HA and MA, and I have RB, I have RC. What I'm going to do is I'm going to take this portion out. I mean, of course I can consider this, but I mean, to simplify my workout, I can omit this, because say if you look at this CD, there's a 30 kilonewton load acting at 4 meters, so that is going to apply a moment. So it's going to apply a moment in clockwise direction, that is 30 into 4. So 30 into 4 is a moment acting clockwise, and the internal resistance is counterclockwise, that is 120 kilonewton meter. Okay, so I simply transfer this to 330 kilonewton load acting at 4 meter into a moment at C. Okay, simple. So now this is my structure now. So I have here 6 meter and this distance is 9 meter. So if I consider 2 segments, AB, BC, so if I consider segment AB, so if you consider AB segment, you can have the equation MAB is equal to, so that is a moment here. Okay, so MAB, here you have MBA, here you have MBC, here you have MCB, and then you have the load acting here. Okay, so if you consider MAB, 2EI over L is 6 for segment AB. Okay, segment AB, so AB, so here MAB, here MBA. Okay, and there will be, because it's loading, there is going to be rotation here, and so you can have theta and all. So 2EI over L is 6, 2 theta A plus theta b minus 3 psi and plus fixed end moment AB. So now if I rewrite this to EI equals 6, and theta A is, what is theta A? Theta A is the slope at A. There cannot be any slope at A because it's a fixed support. So theta A is going to be 0. Theta B, there will be some slope at B because it's a pin, so it can rotate. And 3 psi is appearing if you have any sort of a settlement of the support. There are no mention about settlement of support, so we'll put that one 0 plus fixed end moment. So fixed end moment AB is 0. The reason is there are no load acting. There is no load acting on the segment AB, so there is no fixed end moment. So MAB is 2EI theta B over 6. And if I derive MBA equation, 2EI over 6, 2 theta B plus theta A minus 3 psi plus FEM BA. So with the similar consideration, 2EI over 6, 2 theta B will be there, and this is 0, this is 0 plus 0. So now this becomes 4EI theta B over 6. So these are the moments. So there is no, due to rotation you can have some sort of a moment at those ends, and there are no external loads, so there will be no other moments. If you consider segment BC, so then in BC segment you have MBC and MCB, and you have the load that is 10 kilonewton per meter acting on it. So if you consider MBC, 2EI and L is 9, 2 theta B plus theta C minus 3 psi plus FEM BC. So here theta B is not 0, theta C is not 0, but psi is 0. So 2EI over 9, 2 theta B plus theta C minus 0. Now there will be fixed end moment because there is a load acting on this. So FEM BC is, for a uniform distributed load, fixed end moment is, you can see here, this will be given this chart. If you have a both ends fixed and uniform distributed load, then your more fixed moment is W squared over 12. So I can substitute W squared over 12. So W is 10. So W is 10. L squared is 9 squared over 12. And it's positive because it's counterclockwise direction. So this one is 4EI theta B over 9 plus 2EI theta C over 9 plus this is 810 over 12. So 810 over 12 is, so 810 over 12, 67.5. And if you consider MCB, 2EI over L is 9, 2 theta C plus theta B minus 3 psi plus FEM CB. So here 4EI theta C over 9 plus 2ei theta b over 9. Psi is 0. Then FEMCB also, it is clockwise w squared over 12. So this is going to be minus 67.5. Minus is because it's clockwise. Now these are the set of equations. Now we need to, if we want to solve this one, we need to get the equilibrium conditions. Now if you consider the support A, it's a fixed support, it can carry moment. So there can be net moment acting at support A. But if you look at support B, that is a pin roller. At a roller support, you cannot have any net moment acting on it. So there is the MB acting, there is the MBC acting, and the sum of those two should be 0 because it's a roller. Similarly, at C also sum of these two moments should be 0. So if we consider the equilibrium conditions, if we consider equilibrium conditions, so MBA plus MBC is equal to 0. So MBA, this portion, plus MBC is equal to 0. So MBA is 4ei theta b over 6, and MBC is 4ei theta b over 9 plus 2ei theta c over 9 minus plus 67.5 is equal to 0. So now this is the first equation. So this is 1. The second equilibrium condition is that at C, MCB plus 120 is 0. So MCB plus 120 is 0. So MCB, I put 120 because it's counterclockwise. So MCB is 4ei theta c over 9 plus 2ei theta b over 9 minus 67.5 for MCB plus 120 is 0. This is the second equation. Okay, so this is the second equation. So now if you consider these two equations, we have two equations and two unknowns. Ei is constant. So let us put this way: ei theta b is equal to x, ei theta c is equal to y. So this will make it more familiar. So now 4 over 6x plus 4 over 9x plus 2 over 9y plus 67.50. This is equation 3. Then 4 over 9y plus 2 over 9x minus 67.5 plus 120 is 0. This is the next equation. So now using this equation, you see a familiar values like x and y, and so we can solve this and find the unknowns x and y. So here if you consider these equations, 4 over 6 and 4 over 9, so we can bring it to common base 18, and this is 12, 8, 12 plus 8, 20. Okay, so x plus 2 over 9 y is minus 67.5. So this can be rewritten as 20x plus 4y is equal to minus 67.5 into 18. So that is minus 67.5 into 18 minus 1050. Okay, so this is the rewritten equation 3. Now if you take equation 4, here you have 4y plus 2x is equal to 67.5 minus 120, and multiply that by 9 minus 472.5, that is 4. So these two equations, if you solve, so if you subtract 4 from 3, y will cancel off, so 18x is equal to minus 1215 minus 400 472.5, that is 742.5 minus, and x is equal to minus 41.25. So if I substitute x is equal to minus 41.25 here, y is equal to minus 472. 41.25 into 2 is 82.5. So that is 390. So minus 390 divided by 4. So minus 97.5. Okay, minus 97.5. So if I substitute x is equal to 41.25 here, it becomes minus 97.5 for x. So having that, so it is ei theta b is equal to minus 41.25. Ei theta c 97.5. If I substitute these in the equation, I can obtain MAB and MBA and MBC and MCB values. So substitute values are equations. So MAB is equal to, from this equation, 2 theta b over 6. Okay, so that is 2 theta b over 6. So that is 2 over 6 into minus 41.25. Okay, so that is, if we divide 41.25 so that becomes minus 13.75 kilonewton meter. MBA is 4 EI theta B over 6. So that is 4 over 6 into minus 41.25. That is double on this into 27.5 minus 27.5 kilonewton meter. And if you get MBC, it should be MBC is 4 EI theta B over 9, 2 EI theta C over 9 plus 67.5. So 4 EI theta B over 9 plus 2 EI theta C over 9 plus 67.5. So if you substitute the values in the equation, so if you substitute 4 into minus 41.25 so that is 4 into minus 41.25 into 4 divided by 9, so that is minus 18.33. Here minus EI theta C 97.5, so 2 into 97.5 divided by 9, so that is 21.67 plus 67.5. So 18 and 21.67 in plus 3, 22. 18 plus 22 is 18 plus 22 is 40. So 40 means is 60 minus 40 plus 67.5, so that is plus 27 point. So you can see that MCB is MBA is equal to MBC. So MBA is 27.5, MBC is 27.5. So when you add these two, it becomes 0. So kilonewton meter. So similarly, if you substitute, MCB will become, MCB is 4 EI theta C over 9 plus 2 EI theta B over 9 minus 67.5. Theta C over 9 plus 2 EI theta B over 9 minus 67.5. So when you substitute this value, you will get a value like minus 120 kilonewton meter, because this sum of these two should be equal to 0. The sum of MCB plus 120 is 0. So MCB should be minus 120 to make sure the beam is in equilibrium. So we have got the end moments. Okay, so we got the member end moments, and reactions we need to find. So to determine the reaction, say if you consider the AB, RA, HA and your moment AB is minus 37.25. So minus means it's a clockwise 13.75, and here you have RB1 because you break this into two, right? So the other part is RB2 and RC. Okay, so RB1, RB2. So RB1, then you have the moment MBA, that is 27.25. So that is also clockwise 27.5. Then if you consider RB2, here you have 27.5 plus because it's counterclockwise, and here you have clockwise 120, and then you have another 120 acting outside, and then you have the loads of 10 kilonewton per meter. So now what happens is, if you take this segment 1, is in equilibrium and HA is 0, then you have two equations, two unknowns, two equations, you can find those two. So if you balance vertically, RA plus RB1 is 0, which means RA is equal to minus RB1. And if you take moment by A, so you take moment by A, sum of all the moment is equal to 0. We have 13.75 is the moment acting there, minus 27.5 acting here, and plus RB1 into the distance is 6 meters. Okay, so 6 meters. So 13 by and RB1 into 6 is equal to 0. Okay, so that is the equilibrium equation. Okay, so now we can find RB1 is equal to 27.25 minus 13.75, so that is 5 minus 13.75, that is 13.75 divided by 6, 2.29. So RB1 is 2.29 kilonewton. Okay, the RA is minus 2.29 kilonewton. So this is the reaction RA, RB1 and RA. Then if you take the next part, you can find the segment 2. We can again do the same thing. You balance vertically, RB2 plus RC minus 10 into 9, that is the load acting on this, is equal to 0. So RB2 plus RC is equal to 90. Then if you take moment by B, then RB2 cancels, so you have 27.5 counterclockwise minus 120 clockwise. Okay, 120 clockwise. Then you have another 120 counterclockwise. Then you have the load 10 into 9, 90, so that is acting counterclockwise minus, so the 90 is the load and the effect of the load is at the middle, so 90 into 4.5 is equal to 0. So and you have to consider the RC into 9, right? So that is also missing. So RC into 9. and so the 90 is the load, 90 into 5, then plus RC into the distance 9 is equal to 0. So this cancels off. So 450 minus 27.5, so 422. So 9 RC is 422.5. so RC is, you need to divide that by 9, 46.94. so RC is 46.94. So then you can find RB2 is equal to 90 minus RC. So 90 minus 46.94, that is equal to so 90 minus 46.295, 46.9, 43.05 kilonewton. So these are the reactions and the moments for the, so member and moments and reactions we have calculated. So when you plot a complete beam, you have to add RB1 and RB2. so RB1 is 2.29 and RB2 is something 43.05. when you merge those two, you can add those two. So this is how you solve this problem. And we can also plot shear force and bending moment for these small segments. We'll see that in later exercises.